Hello dear audience, my name is Mert Murat Kurt and I'm going to explain the confocal laser scanning microscopes Leica's patent, which is TCS SP8. So this presentation includes the significant parts of the confocal laser scanning microscope system and the working principle basics and system properties. And this Leica laser scanning microscope is known as option machine, so it has so many options. I would like to tell the options in options part, and I will tell the advantages of the system and how I have some ideas to develop. So I will explain them in fifth part. So the first part of the significant parts of microscopic system, of course, it has some objectives that can immersion oils and glycerols, waters can be injected at the point of the objective, and it has the main part Leica's TCS scan head. This is the scan head, and inside of the scan head there is AOBS and dichroic mirror. It depends on the examination. We can choose this dichroic mirror or AOBS. So this is some centerpiece of the scan head. So this is the Leica TCS SP8 scan head. With its revolutionary design, it provides high-performance optics about standing transparency and optical throughput. Leica's patent here, AOBS Acousto-Optical Beam Splitter, allows you to separate fluorescent light without the bandwidth limitations of traditional dichroic beam splitters. Use a broad variety of light sources from ultraviolet to visible and infrared, or take advantage of Leica's proprietary white light laser technology. The three-mirror scanning system is engineered to maximize imaging precision, discover the largest field of view, best-in-class flatness of field and homogeneity of illumination. Switching to resonant imaging of 12 kHz, you can work on more than 420 frames per second. A purely optical field rotation system guides the high-speed scanning beam to any angle you need. For example, when imaging nerve cells in a living tissue culture, this makes the Leica TCS SP8 the instrument of choice for neurosciences. Leica's state-of-art hybrid detectors are available in both descant and non-descant versions. These are ideally suited to multiphoton imaging. The detectors work in synergy with next-generation CS2 objectives to give perfect colocalization and optimized image acquisition of structures deep within tissue sections. Components work in synergy with the AOBS, the white light laser, the spectral detector, and Leica's unique spectral detector. A clear glass prism is the dispersive element. This overcomes absorption of integrating setup. Polarization of the fluorescent light is irrelevant for the prism, and throughput of light is maximized at almost 100%. The Leica spectral detector separates the different fluorescent colors of your sample to single photomultiplier or hybrid detectors, depending on the intensity of the light which you choose to gain. Treat each fluorophore separately to optimize its representation in the resulting image. True spectral detection ensures true imaging of your sample without compromise. So let's move on to the option part. As I said at the beginning of the presentation, it is known as the option machine. So it has so many features, additional features. Let's start with it. So it is known as the SMD feature. It is high dimensional imaging and analysis. So this is a mouse diaphragm. The red fluorescence is the muscle signal, and the green one is the neural signal. Yes. So this is a high dimensional imaging and analysis. So let's move on to the other one, MP, TCS SP8, MP, additional feature. So it enables to look deeper in the sample. So let's read it. So most advanced infrared lasers up to 1300 nanometers with pre-chirped femtosecond lasers and optical parametric oscillator, expanding deep tissue imaging into the red. So this is 600 micrometers deep. So the depth will be rise. The other feature is motorized optical objective. So this is motorized correction color for best optical performance in thick tissues. As we see, there is a motor and there is a wheel which changes in refractive index of lens group correcting. And in the tip of the objective, there is a front lens. So this is a motorized objective. Yes, there is a high precision detector, also can be bought. And this is super sensitive imaging. It enables to take images super sensitively. So this is a confocal imaging, which is 200 nanometer in microscopy, and this is a super resolution, which is 140 nanometer. This is called high resolution. It's a feature in Leica's optional parts also. And let's move on to nanoscopy scale. This is 30 nanometer. This is 30 nanometer, and this is called the STED feature. If we compare the confocal image and the STED with a 3D structured, reconstructed human tissue, this is a live tissue cell image with 1 micrometer, you can see the difference in super sensitivity. And as we see, this is a cell 2 in confocal image, high resolution and STED. We can see the difference clearly. So super sensitivity is an optional part too with this head. So if we look at the slow detector, normal conventional method, these are waves. But if we look at the fast rapid detector, these are so rapid, like notch signals. This is the fastest one, point by point, and this is the photomultiplier tube conventional method. It has so many advantages in this Leica TCS SP8 confocal laser scanning microscopy. So this is a lateral section of muscle fiber. The purple ones are muscle fibers, and this is the coronal section of mouse nasal cavity. This is high resolution. So it has highest photon efficiency for live cell imaging and publication ready image. This is a good advantage. And fastest confocal point scanning for new high speed experiments and rapid 4D time-lapse recordings. And the third one, ready for the future with an open upgrade path and turnkey solutions for super resolution. As I said, these are so highest resolution images on multi-photon imaging and coherent anti-Stokes Raman scattering and single molecule detections. My idea is this. I read some reviews for the Leica TCS SP8, which the biologist professors wrote them, and they wrote that the scanning system is low scanning rate. So how can we make it faster? Maybe a NIPCO disk can make it faster. And they wrote that the system is less sensitive than spinning disk confocal microscopy. So we can add to this part behind the objective a NIPCO disk with a camera. And of course, if we add to this place a NIPCO disk, we have to motorize this stage with piezoelectric materials. So this is my idea. It can be applied easily, I think, but I don't know, maybe they tried it. So it can be fastest examination ever. So these are my references. All of them are brochures and user manuals of Leica's TCS SP8. I read them and made the video. So thank you.